Okay, so this skeleton is going to be quite similar in that we're going to be left with less than the octet. And so now we're going to have to form a multiple bond by pulling in a lone pair and making a bond. So we have a choice here. Should we take the lone pair off nitrogen or should we take the lone pair off oxygen? What do you think is going to be more willing to give up its lone pair, nitrogen or an oxygen? Nitrogen. Nitrogen should be more willing to give up. Why? It's less electronegative. You know, oxygen is more electronegative, so it's going to hold on to the electrons more tightly. And so the first step should be easy. We'll take a lone pair off nitrogen and make a double bond here. So we'll get a nitrogen-nitrogen double bond. It's going to leave two lone pairs here, and then the oxygen out here. But we're still short of an octet. And so we have a choice. Should we take it again off nitrogen, or should we now take it off oxygen? Nitrogen's already sacrificed one lone pair. Should it sacrifice another, or should we take it off oxygen? We could take it off nitrogen, or we could take it off oxygen. We should just try both and see at this point. Because if we take it off nitrogen, then we'll end up with this structure. A nitrogen-nitrogen triple bond, and then a single bond to the oxygen. Now, everybody has an octet. You know, this nitrogen has an octet, nitrogen, and oxygen. However, if we took it off the oxygen instead, we get a different structure. So if I take it off the oxygen, I'm going to go right here. If I take it off the nitrogen, I'll go down here. And so let's take it off the oxygen and then leave the nitrogen alone. And so we end up with something like this. There. This is nice because it's symmetric, you know, two double bonds. This is a triple and a single. And so what is better in this case? The triple and the single or the two double bonds? Well, everybody has the octet, right? And so let's take a look at the formal charges to verify. And so looking at the formal charges here, this nitrogen is 0. This nitrogen, 1, 2, 3, 4, is plus. This nitrogen, or excuse me, this oxygen is minus. You know, I know a way to get rid of this minus formal charge on oxygen. I'll just take another lone pair here. Maybe I should have gone triple and double. Because take a look at what happens if I go triple-double. If I go triple and then a double here, then all the formal charges go to 0. So this nitrogen 0, this nitrogen 0, this oxygen 0 here. And so all the formal charges are 0. Formal charges, we'd have to separate charges. Separating charges creates a voltage. A voltage requires work to do that. That is, the oxygen has to ionize or take an electron off nitrogen. Keep it. And so this one looks good because all the formal charges are 0, but there's a problem. The problem is what? The octet. And so we can automatically eliminate this because nitrogen cannot expand its octet and be too costly in terms of energy to do that. Okay, so those are the formal charges here. The formal charges here are going to be minus, this is going to be plus, this is going to be 0. And so the formal charge, the magnitude of the formal charge is the same, a plus charge on the nitrogen. The difference is, where does that negative charge go? Where does the extra electron go? And so looking at this, the extra electron is going on oxygen, giving it a negative charge here. In this structure, the extra electron is going on nitrogen, giving it the negative charge here. And so ignoring the bonds, you know, because this is more symmetric, but that doesn't really matter. Let's take a look at the charge. You know, and so one way of visualizing what's happening here is you have a tug of war for electrons, oxygen versus nitrogen. Who wins that electron? You would expect oxygen to win the electron because oxygen is more electronegative. And so we say that this is the most stable structure for nitrous oxide here. But not everything's so black and white, though. Because yes, it is true that oxygen is more electronegative than nitrogen. But how much more electronegative? Not much. The three most electronegative elements are fluorine, oxygen, and nitrogen, in that order. And so fluorine's a 4O, oxygen's a 3,5, nitrogen is a 3O. And so a 3,5 versus a 3O, is it a one-way fight or one-way tug-of-war for that electron? You know, when the delta EN between oxygen and nitrogen is only 0.5. Is that a significant? Is that delta EN? Is that a large delta EN, 0.5? No, we said that's a negligible delta EN. And we would say that, you know, the electronegativities of those are comparable, so nitrogen-oxygen bond isn't very polar. They both have pretty equal strengths in the tug-of-war. And so what we can do here is, yeah, this one should be more stable because oxygen is more electronegative, but nitrogen is also highly electronegative. And so what we end up with is this. We end up with unequivalent resonance forms. In other words, we can't ignore this structure completely. For bicarbonate, we ignored one of the three structures because in terms of energy, it was highly unstable compared to the other two structures. And so we threw one of those structures out. We aren't going to throw this structure out. This structure is significant. And so basically, the most stable structure should be like this, with the negative charge on oxygen here. But we could also rearrange the electron density to come up with this structure. Where we have the negative charge on nitrogen. And there's always a positive charge on the central nitrogen here. But you wouldn't expect it to be 50-50 because oxygen is slightly more electronegative. And so in the bicarbonate, we narrowed it down to two structures. Those two structures were degenerate. What does degenerate mean? Degenerate just means that they're the same energy. Here, these are non-degenerate structures because these two structures have different energies. But not hugely different. This one is a little bit more stable than this one. And so what we could say is we'll just take a guess. We're going to guess, yeah, oxygen's more electronegative, so we'll say maybe 80% it's like this, and 20% it's like this. Versus in the previous one, we did a 50-50. 50% this, 50% that. This one's going to be an 80-20, or maybe it's a 70-30, you know, because nitrogen and oxygen are pretty evenly matched. Maybe it's a 60-40, you know, close to a 50-50, because maybe it's a pretty even tug-of-war. But we'll just guess at 80-20. And so what do we do when we do a hybrid structure? When the hybrid structure comes along, then we bias these depending on which one is more stable. And so if this one's slightly more stable, then the hybrid should be more like this. That is, the nitrogen-nitrogen bond, you know, is between a double and a triple. If it were a 50-50 mix, we'd call it 2.5. You know, because a double we call it 2, that's called the bond order. A triple we call it 3. And so if it's 50-50, it would be halfway between the two. But here, it's more like 80% more towards the triple. And so when we do this, the hybrid, oops, let's draw it down here. The hybrid is going to have a double that's always fixed. And over here, it's going to have a single that's always fixed. but the extra electrons are going to be split between the two bonds. When we spread it out between two bonds, we call it delocalized, or delocalization. And so we spread out the electron cloud over both these, like that. And so 80% more here and 20% less here for the electron density. And so what the bonds come out to be is it's closer to a triple here, and so we'll call it a 2.8 bond. It's 80% closer. And so we're going from 2 to 3, and so we'll just call it 2.8, 80% of the way there. This nitrogen-oxygen bond is closer to a single than a double. If it's closer to a single than a double, we'll call it a 1.2 bond. And that shows it's much closer to a single bond. And now, there's a lone pair that's fixed on the nitrogen, and there's two lone pairs that are fixed on the oxygen. And then there's one lone pair that's spread out over both atoms, or delocalized over both atoms. And it's going to be an uneven delocalization, because what we're going to do is we're going to do 80% of the lone pair should be on oxygen, right? And so oxygen is going to be closer to -1 than nitrogen. And so what we'll do here is we'll put more electron density on oxygen, and that's going to give it a different formal charge. The formal charge on oxygen over here we'll call -0.8. And the formal charge on nitrogen over here we'll call -0.2. And the formal charge on the central nitrogen stays the same at +1. And so this is resonance hybrid, but with an uneven contribution from the resonance forms, not a 50-50 contribution. Let's say we guessed it was 70% this, 30% this. You know, if we guess 70% this, then it'd be a 2.7, 1.3. You know, it's getting closer to midway between. If it were 50-50 mix, then yeah, it would be 2.5, 1.5, -0.5, -0.5. Formal charges. So we're taking a guess there. We're saying that the hybrid should be biased towards having the negative charge on oxygen versus having the negative charge on nitrogen. And so we showed it biased towards that. You know, I'm speaking up. But that's a total guess. In order to get a more accurate thing, we'd either have to take measurements of the charge on the atoms, or we'd have to do some theoretical calculations to figure it out. Okay. And so this is what we'd have. Nitrous oxide, what is it, an oxidizer or a reducer? Or both? The nitrous oxide is both, because the nitrogen's +1. At +1, it could either gain electrons or lose electrons. Well, here's nitrous oxide. Here. But are they showing the bias, you know? Are the two resonance forms degenerate? That is, are they the same energy? No. And so we tried to bias it a bit because we preferred this one because this one had the negative charge on the oxygen versus this one, which has a negative charge on the nitrogen. So we biased it 80% there. But how can we get the number? There are different ways we can get the number. The bond lengths, you know, like triple bonds have a certain length, double bonds have another length. So we could use the bond lengths to kind of predict, you know, what the percentages are. Other ways, you know, we could do some theoretical calculations of the charges, etc. But the IUPAC name for this, which is the International Union Pure and Applied Chemistry, calls it dinitrogen monoxide. But there are other names for this: laughing gas, sweet air, protoxide of nitrogen, hyponitrous oxide, or just plain old nitrous oxide. Nitrous oxide is a common name. And so what is nitrous oxide used for? Let's see. Used for a whole variety of things. It's a non-flammable gas, meaning it's not a very good reducing agent, but you probably can burn it at high temperature. So it's used in rocket motors. I wonder if it's used as an oxidizer or reducer. The fuel in rocket motors or the oxidizer? Internal combustion engines, aerosol, propellant, medicines, etc. In rocket motors, nitrous oxide can be used as an oxidizer. Advantages over other oxidizers is it's non-toxic, but also stable, easy to store. Secondary benefit, it can be readily decomposed to form breathing air. So if nitrous oxide decomposes, it will form nitrogen and oxygen. Nitrogen and oxygen is air. Its high density and low storage pressure make it a good oxidizer, I guess. Let's see. It's used in engines. You know, a lot of people in racing put nitrous oxide into their fuel. Allows the engine to burn more fuel by providing more oxygen. So nitrous oxide acts as an oxidizer in engines. Probably it decomposes and forms nitrogen and oxygen. And the additional oxygen helps combust, providing excess of oxygen. Nitrous oxide. Aerosol propellant. It's approved as a food additive. Aerosol spray propellant used in whipped cream canisters, cooking sprays, potato chips. Nitrous oxide won't burn at low temperatures, but at high temperatures, nitrous oxide can burn. Used in medicine as an anesthetic. Used in dentistry since 1844. Recreational use. Some people use it for recreational purposes. I don't know if that's legal or not legal. Mechanism. So there's a lot of information here, but one thing is they don't talk much about the structure, do they? They don't tell us how it's biased, you know, which resonance form, you know, what percentage. But whatever theory we have, you know, it has to agree with experiment, and so we look at the charges that are observed on those atoms and we can figure it out. Okay. Actually, what we're going to do is we're going to do some theoretical calculations on nitrous oxide. And you know, the great benefit of doing what we're doing here is this doesn't require any kind of theoretical knowledge. You know, do you know how to solve the Schrodinger equation? Or can you do any quantum mechanical calculations? No. You know, well, we don't have to. You know, we can figure out a lot about the charge based here. Now, how accurate is it? Well, we don't know because I'm just guessing here on this, and this could be a good guess or it could be a bad guess. But we happen to have some software here that does quantum mechanical calculations. The software is quite expensive. If you were to buy it standalone, it's like $5,000, I think, roughly. But there, you don't really have to know quantum mechanics. You just build the structure and ask it to do calculations for you. And so we're going to input nitrous oxide in there and see what kind of charges we generate here. You know, is this pretty accurate or is this far off? You know, with an 80% contribution of this structure, 20% contribution of that structure. And so we'll actually do some calculations. Those calculations, of course, have to be verified with experiment because whatever theory we have must agree with experimental fact. Okay. All right, let's go on to the next part of this. The next part of this is VSEPR, valence shell electron pair repulsion theory. And we're looking at geometries. There are two types of geometries that we're going to see. There's something called group geometry. And group geometry deals with groups of electrons on an atom. And so if we have a single electron on atom A, some generic atom, this single electron is called a group. And a single electron like this, you know, there's going to take up some space because there's going to be some repulsion. So the electron's negatively charged. So this is just to show, you know, how much volume or what kind of repulsions we get from that. Single electrons are called free radicals. You know, free radicals are highly unstable. They'll either want to form a pair of electrons or they'll want to form a bond. And so if we form a lone pair's got twice as much electrons, so it's going to require more space. It's more breathing room around it. And so lone pairs occupy more space than radicals or single electrons. What if we have a single bond? In a single bond, you know, we'll have an A-B, you know, two atoms bonded together, and then we'll put the pair of electrons as a line like that. Since we still have two electrons, does it still have the same space requirements? No. On atom A, it's going to have less because now the electrons are being pulled away from atom A. As electrons are being pulled away from atom A, you know, this thing's going to compress and go up, and so space requirements aren't going to be as significant. And so lone pair occupies more space on atom A than a bond does. Well, that's a single bond. When we compare it to a double bond, you know, double bond has 4 electrons in here. The double bonds are shorter, turns out. That's what make it like that. Well, double bonds and lone pairs are comparable. You know, they take up about the same amount of space around atom A. And then we'll have the triple bond. The triple bonds will take up the most space. About atom A. And it's the space requirement that's going to dictate the shapes of things. These are called groups. So a lone electron is a group, a lone pair is a group, a single bond is a group. A double bond consists of one group, the double bond group. A triple bond, again, is just one group, a triple bond group. So what we're going to do is we're going to generate something called the group geometry. Group geometry has another name. It's also called the electron pair geometry. So group geometry, electron pair geometry. Well, the simplest is if I have two groups of electrons about atom A. There's one group here, another group here. And so this group can be any of these, like a single electron or radical, lone pair, single bond, double bond, triple bond. The same thing with this. And so we got two groups. The two groups will want to minimize repulsions between each other because all these are regions of negative charge density. There's going to be a negative charge cloud or electron cloud. And so to minimize the repulsions between the two electron clouds, we want to arrange them like this. We want to arrange them 180 degrees apart from each other. And so this is called a linear group geometry here. We got a group geometry, and then what we end up looking for is a molecular geometry. the molecular geometry is different than the group geometry because the group geometry is just looking at all those as groups, but for molecular geometry, we're just looking at the geometry of the bonded atoms. What happens is, even though there's going to be repulsions between the lone pair and the radical, you can't pinpoint the electrons here. What we can do is we can pinpoint the atoms. And so when we look at the molecular geometry, we could have something like this, where A is bonded to B and C by single bonds, or maybe there's a double bond here with B and a single bond with C, or it could be a triple bond and a single bond. Well, the triple bond and a single bond, this is nitrous oxide here. Nitrous oxide is going to be what we call linear because the two groups on A will want to try to get as far apart as possible. And these two groups are going to adopt a 180. Even though the triple bond is going to take up more space, still 180 is going to be the maximum distance apart from each other. The nitrous oxide is going to be like this. This is one resonance form of nitrous oxide. The other resonance form of nitrous oxide had two double bonds. And so it's still two groups because we can't split up the double bonds. The double bonds have to be taken as a unit. And so we have two units here, two double bonds. And so again, this is going to be 180. And so what we call this is the geometry of the bonded atoms, in this case, is going to be linear, just like the geometry of the groups over there. And the angle is going to be 180 degrees. And so an example of this would be BEF2. BEF2. Well, the first thing is this Lewis structure right? Lewis structure doesn't look right because something's missing. Do you know what's missing? Yeah, the octet on beryllium. Beryllium doesn't have an octet. So what can we do about that? Well, it's simple. What we do is we form more bonds. And so let's try to get that octet on beryllium. So if I form one double bond here, by taking a lone pair and dropping it into the bond, I'll end up with this. But I'm still shy of an octet. And so probably the best thing is not to form a triple and a single. Probably the best thing is to form two doubles. The fluorines are the same. And so let's go for two doubles. Like that. And now everything has an octet. But just because we have an octet, we still have to check the formal charge to make sure the formal charges are reasonable. And so if we look at the formal charge here, fluorine is 1, 2, 3, 4, 5, 6. It's supposed to have 7, so it's got a plus. Beryllium is supposed to have 2, but it has 4, so it's minus 2. The fluorine is plus. And so essentially, when we're dividing up the electrons, beryllium took 2 electrons, 1 from each fluorine. Does that make sense? You know, if there's a tug of war for electrons, will beryllium win? And not only win, but win over 2 fluorines. No. And so these are ridiculous. This is a ridiculous formal charge. It's a ridiculous formal charge because fluorine's the most electronegative element on the periodic table. And so this would not be stable. In fact, just forming one double bond is too much because here beryllium ends up taking an electron from this fluorine. At least it didn't take it from both fluorines. But still, this is ridiculous because is fluorine really going to give up an electron to beryllium? No. Because here, in this case, it's not like nitrogen and oxygen. Nitrogen and oxygen are kind of close together, right? So it could really go either way. But it's going to be biased more towards oxygen than nitrogen. But here, beryllium and fluorine are so far apart in terms of electronegativity. Beryllium is very weak, fluorine is very strong. And so something like this is not going to happen. And so we come up with a rule in Lewis structures. Fluorine, as well as hydrogen, but fluorine can only form one bond. This is just for fluorine. Chlorine's a much bigger atom. And so chlorine has the possibility of forming more than one bond. This is just bigger. Same thing with bromine. Bromine doesn't have problems forming more than one bond. iodine, etc. But fluorine is a special case and will never sacrifice fluorine's electron for an octet. And so this is just the opposite. We don't even have an octet. We have less than an octet, and there's nothing we can do about it. And so this is the correct structure for beryllium difluoride. It's a molecular compound, even though you'd expect it to be ionic because beryllium is a metal, fluorine's a non-metal. But this is beryllium difluoride, the molecule. And the molecular geometry here is linear. Because when we look at the bonded atoms follow the same pattern, and we have to state the bond angle. The bond angles are always defined by three atoms. So F, B, E, F angle. The F, B, E, F angle is going to be 180 degrees. So it's linear at 180 degrees. If we bring a third group, this would be the third group. We'll just put it here or here. We'll just bring it up from the top. So the third group of electrons, to spread things out, so all the groups as are far apart from each other as possible, it'll have to adopt this geometry. And so this group geometry is called trigonal planar. And so it's a trigonal planar arrangement of groups. Now the groups can be anything. You know, for example, it could be a trigonal planar arrangement, might be a lone pair and then two single bonds. Or it could be three single bonds, or it could be a double and two singles, etc. And so, you know, any of the three groups arranged in this configuration would be trigonal planar. Now, if it's trigonal planar, for the bonded atoms, we have some choices here. If we have, like say, bonded atoms, three bonded atoms like this, then the molecular geometry is also trigonal planar. And so the classic example of something like this would be BF3. BF3, again, boron has less than an octet here, but fluorine will never double bond this. And so it's stuck. And so when we look at it, no, this is trigonal planar as well. And the angle, it's going to be the FBF angle. The FBF angle is going to be 120 degrees. All the FBF angles are 120 degrees. Now, if we have a lone pair in some arrangement of bonds, I mean, we could have a double bond here too. You know, it doesn't have to be singles. But if we have a lone pair and two bonds, then this is going to be what we call bent or angular. And we put 120 degrees because there's another bent or angular with a 109 degree angle. And so this would be something like BF2 minus. BF2 minus, the ion, is going to look like this. Boron's going to have a lone pair here, and then two fluorines bonded to it, like this. And so the group geometry is trigonal planar because we've got three groups, single bond, and a lone pair. But the molecular geometry is not trigonal planar. The molecular geometry, we're just looking at F, B, and F. F, B, and F form an angular bent geometry. So this is angular bent, and the FBF angle here. The FBF angle normally is 120 degrees, and so we call it 120 degrees ideal. But what happens is the lone pair takes up more space. The greater repulsion is because the lone pair are concentrated on boron. And since the lone pair are concentrated on boron, it pushes these two in. And so we see a distortion. And usually the lone pair results in a 2-degree distortion. So if there's a 2-degree here, a 2-degree here, that would be a result in a 4-degree distortion here. And so about 160 degrees is the distorted angle. And so this will be approximately 116. That's a total guess too. a lot of people just say less than 120, but less than 120 can vary from 0 to 119. This is too big of a range. And so to narrow the range, we'll just say 116 plus or minus 4, you know, something like that, degrees. It would be more accurate. BF2 minus. If we bring another group, we'll just stick that on the top. There. Another group, and then I'm going to just rearrange how we display it. And so what we'll do here is with 4 groups, we'll put one group in the plane, a second group in the plane. These groups are going to be separated by an angle of 109.5, and then a third group coming out of the plane and a fourth group going in to the plane. And so this group geometry is called tetrahedral. Tetrahedral has something called spherical symmetry. We'll look at that in more detail. And so what we're going to do is we're going to take a break. Sometime during the break, go and check out a model kit over there. I'm going to build some models, please. Okay. So I'll stop here.